What is the most satisfying sound on the planet? Somebody on YouTube making an ASMR video that sounds more like Anthony Hopkins in Silence of the Lambs?
To me, whispering into the microphone is really creepy.
I don't think so. Instead, I think it is the sound of freedom. Freedom of a freewheel on a bike, that is. There's just something about that sound. So today I thought we'd try and recreate that sound in a 3D printed part, and if we succeed, you will be able to download it too for use in your projects or for a fidget to play with as well. So let's find out if it's possible to reproduce that pleasing click sound in a 3D print. There are lots of clicky toys out there and they're fun, but none of them make the right click sound that we have on a bike freewheel. And what I'd like to do is create a working ratchet that we can use on any of our projects to retain its position while also giving us that amazing sound with each rotation. I've searched and I can barely find a picture of a working freewheel, let alone a full design, so I think it's time to create our own. This could be done fully 3D printed, including the springs, and maybe even printed in place, but we're going to use 3 small springs for ours instead, since that's what springs are for. We're also going to want a bearing so we get a smooth, low friction spin. That it isn't completely necessary, it's just going to improve the function a bit. So Fusion just updated to something they're calling intent-driven designs, and if you start out like I did with the wrong type, you can change it easily just by going to the document settings and click on convert and change it to hybrid so we can then use components in our designs. Again, not really critical, but in my case, I wanted to see what it would look like if it was rotating, and I needed to use components for that. To start with our design, we need a rim, which is going to become our internal ratchet or our gear. There is an option to do external or internal, but external, I think we can have more divisions for the teeth, and I like the idea of having the maximum amount. I'd also like it to be small because if the small version works, the bigger version can be scaled up easily. So I'm going to go with 62 millimeters for the outside of the rim. We'll offset 5 more circles, one for the root of each ratchet tooth, one for the peak of each tooth, and one for the reference for our carrier or the hub in the center, and make them into construction lines. The other 2 will be for the internal and external sizes of the bearing that we'll be using, and those 2 will be standard lines. It's a good idea to also set some parameters so we can easily change the amount of teeth later on, or the diameter, or whatever we want to change. So one of the important ones that I have is called division, and with that one set, we can draw in 6 straight construction lines, 5 of them coming out from the center of the circle. 2 of them are going to be slightly off from the center line, extending to the inside or the peak of the ratchet. 1 coming out that we'll use in a minute, and we will add a 5 millimeter diameter circle to the end of that one. And then 2 more extending to the inner construction line circle, which we call the reference circle, and then 1 more line nearly parallel. We'll use angles to help constrain them, so 120 degrees between the reference line, 15 degrees to that nearly parallel line, 25 degrees to the line with the 5 millimeter circle on it. We'll then use 360 degrees divided by the division parameter to set the final angle. So now we can work on the teeth. We'll need a straight line for what I'm calling the relief angle. It could also be the pressure angle, and then we'll need an arc, and I'm setting the radius of that arc to 40 millimeters. Unlike a standard gear, the arc here will actually load the spring behind the pawl, giving that nice click sound each time. I'm going to connect the arc and the line with a small radius because it's better to avoid sharp corners here. The center of the arc can be constrained to the vertical center line, and the outside of that same arc can be constrained tangent to our root circle. We're now going to offset that line with a clearance of 0.1 millimeters and then extend that arc out, and we can have it meet at the tangent of that small 5 millimeter circle that we created earlier. And then we can draw the housing around what will become the pawl. So the housing around the pawl here allows it to float, and because it's essentially its own bushing, it's very small, which I think is also important here. For the best function, the pivot point for the pawl needs to be as close to the outside as possible. And because we are just going to be slightly inset from that, because we're 3D printing this and it's not made of steel, so I need a little bit more beef, that's where that relief angle comes in that we set a little bit earlier on. It's going to allow the pawl to spring back and seat really quickly. For the carrier, we're looking for something that supports the force being transmitted through the pawl and into that carrier. So a nice beefy triangular shape works really well here. And we're going to have it come down and connect to where that straight line meets the reference circle that we created earlier. Now all we need to do is add a spring, and I originally experimented with some larger springs here, but with this design, a very short and small spring seems to work the best. And what's important here is that when the pawl is seated, we want to have almost no compression on that spring, because if we did, it would load that spring a little bit too much as we rotate it, causing a bit of excess friction and for the pawl to have a louder and more unpleasant noise. To lock the spring in place, we're going to draw a line up top connecting the bottom of the pawl to the pivot and set a distance of 2.2 millimeters and include a pin size of 2.23 millimeters, which is just slightly less than the inside diameter of that spring. We are going to do the same exact thing on the bottom, first coming down though and making sure that we are parallel to the locating pin that we just created. We'll extend it out to the reference circle as well. Spring length that I'm using here is 10 millimeters, so we just need a number slightly below that so that we have just enough spring pressure for it to work. Now we can use circular pattern and add teeth all the way around in our sketch, and that will be the division parameter that we can reference. And we could also do the same thing for the carrier, and that will be 3 in this case, but if we were to use 2, we'd have 180 degrees instead of 120 degrees. We just need to extrude those shapes, and then we can make the pin mount circular too by extruding from one object all the way into the carrier and cutting that shape out. Now, I did try and pattern that feature, but Fusion did not like to do that here, so instead I had to do a sketch and extrude it 3 different times. It's only mildly annoying. Because of the way that I patterned the teeth, we will also need to remove the sharp point that's on there. That's just an area that's going to wear more quickly, so a very light fillet on those edges too is going to help. One thing that's important to do that I rarely see done on any 3D prints is to lightly chamfer tops and bottoms, especially the bottoms. That's because the bottom layer really isn't always exactly perfect. Sometimes there's a bit of elephant's foot. So to make sure that it's not an issue, we will add a light chamfer there. And of course, that also happens to look good. I also revolved a small section to help capture the pawls vertically so that they can't work their way out. So let's go ahead and print a set to see how it turns out. And I am going to be printing using PLA. Something stiff, I think in this case, is going to be more similar to what we would have with metal. I'm going to be using 0.4 millimeter nozzle, but I think an even smaller version could be done with a 0.2. This is the knob, and unfortunately I was supposed to have flipped it 180 degrees, so that I had to reprint. Everything else looks like it turned out great. So these arrived just in time. I was about to finish up the video and these smaller springs came in. So these are ones I ordered from Maker World. And they are basically half the length. So I'm not 100% sure which spring I prefer. I think to my ear this one sounds a little bit better, but I don't mind either one. Both of them sound pretty good to me. So we have a little cap that can go on there and that becomes a fidget. This will snap into place. The whole point of this is not to create a fidget, it's just to give people something to download that they can play around with and maybe even include it in their own designs. So it's the moment of truth. Let's see how the bike sounds, the freewheel on the bike sounds compared to what we have. It's pretty similar, not too far off. So that's the really short spring. So as important as the sound actually is, it is much more important for it to actually function properly. And I think it is functioning perfectly. But if you have ideas on how to get the sound here in a 3D print in plastic, a little bit more reminiscent of what we have in the bike, please let me know in the comments below. I think 3D printing is only going to get more popular, and I think it makes sense to have these types of mechanisms available to everyone so they can include them in their designs as well. So this will be linked below in a fidget format, and I'm also including the Fusion file as well for anybody to use. And of course, it's parametric also. As always, check the links below for my top rated 3D printers. If you're in the market, those links do help to support this channel so I can keep making this type of content. And let me know if you like these types of videos too, so I know if I should make more. And thank you to each of my patrons for helping to support this channel. Thanks for watching, take care, and I hope to see you on the next one.